Okay, so we'll start this module on graph algorithms, and so we're going to see what is called some data structures, kind of things with graphs and algorithms to build them, and then some properties and theorems associated with this. So we'll start with what's called a minimum spanning tree in a graph. So you all know what a graph is from the previous course, data structures. So a graph is a set of nodes and edges. Now the edges could have some weights. So this could be a graph uh, of 6 nodes and edges connecting these nodes, and the edges could have some weights. So an application of this could be the distances between the cities. So the cities could be nodes and edges could be the roads connecting the cities, and the distance between two cities could be the weight of the edge connecting those two nodes. Now a minimum spanning tree is a tree. So you all know what a tree is again from data structure. So a tree will not have any cycle, means there's only one path from between any two nodes. So a binary tree is a tree. So here looking at what is called a spanning tree. So a spanning tree is a tree that will cover all the nodes like this. So we have 6 nodes in this graph here. So a spanning tree of the 6 nodes should cover all these 6 nodes. Now you could realize this is not the only way to cover or connect all these 6 nodes. You have several edges here, so you could put together some combinations of the edges and connect them so that you can have what's called a spanning tree covering all these 6 nodes. Now depending on the edges that you put together, the what is called the weight of a spanning tree will be different. So in this case, the weight of this spanning tree here is just sum of the weights of the edges, which is 3 plus 1 plus 1 plus 2 plus 3, which is 10. So the weight of this spanning tree is 10. On the other hand, if you come up with some other spanning tree by putting together some combinations of edges, it could have a weight greater than 10. Okay. Now the question is, what is the minimum possible weight of a spanning tree? Now again, this is a tree, no, a graph of 6 vertices. So there is a property. If I have not mentioned the data structures class, you should know this property. So if a graph has n vertices, like in this case 6 vertices, a tree that is spanning all the vertices, like in this case a spanning tree, should have n minus 1 edges. So in this case you have 6 vertices, we have 5 edges. So a spanning tree on n vertices should have n minus 1 edges. So you could put some combinations of 5 edges and come up with a spanning tree for this graph based on the edges given to you in this graph. Now such a spanning tree could have weight 10 or greater than 10. Now why I say it is 10? Because we are going to look at an algorithm that I have run through here, the iterations, and come up with this spanning tree. And that algorithm is guaranteed to give you what is called a minimum weight spanning tree. So a minimum weight spanning tree means you cannot find a spanning tree of weight less than that weight of that minimum weight spanning tree. So in this case, the minimum weight spanning tree, the weight of the minimum weight spanning tree is 10. So that means that's the best possible spanning tree weight you can come up for this given graph. Okay, so you cannot come up with something less than 10. So we are going to look at one algorithm in the class, in the lecture. It's called the Kruskal's algorithm. As part of as an assignment, I'm going to give you another algorithm called the Prim algorithm, for which the working details I'll give you. You have to understand it as part of the assignment and work through an example. So that's an assignment for you based on minimum spanning trees. So make sure you understand all the properties of the minimum spanning trees as we go through, so that the Prim algorithm will be more easy for you to work with. Now there's a very important property of minimum spanning tree or any minimum spanning tree algorithm that will build a minimum spanning tree. So let us use this example to understand that property. So we are going to mostly build iteratively the spanning trees in all the algorithms. So as the algorithm builds the spanning tree, whatever it has built so far is going to be a minimum spanning tree among those vertices that are part of that spanning tree. So in the sense, some algorithm has built a spanning tree of these three vertices, these four vertices, using these three edges. So this is the minimum spanning tree of these four vertices, and the edge weights are 1, 3, 2. And this is another minimum spanning tree of these 5 vertices here with weights 1, 2, 3, 4. So now again, like we are going to do that on a given graph like this. So in the graph based on which the two spanning trees are built, you also have edges connecting the vertices in the two spanning trees, the two minimum spanning trees. So basically it's like two clusters. You have one cluster of vertices here, another cluster of vertices here. Each cluster is a minimum spanning tree. So now you have to kind of connect these two clusters using one edge. So if you connect these two clusters using one edge, the whole thing is going to become one minimum spanning tree. So the question is, which edge that crosses this two set of vertices we have to pick. And it's like a greedy strategy here because we have different edge weights, so it makes very sense that if you pick the edge of the smallest weight to connect these two clusters, the whole thing is going to become minimum weight. Why? Because this cluster by itself alone is minimum weight of weight 1 plus 3 plus 2, 6. This cluster alone is minimum weight 1, 2, 3, 4, which is like what, 10. So you have 4 and 10 as the weights of the two spanning trees here. So I want to connect these two spanning trees so that the whole thing is going to be of minimum weight. Okay. So it makes sense to choose an edge that connects these two spanning trees with the smallest weight. So in this case, I'll pick the edge with weight 2 and connect them. So that is going to be a minimum spanning tree involving this 9 vertices. So to connect these 9 vertices, this is the edge that we should pick to connect this cluster of 4 and 5 vertices and make the whole thing as one minimum spanning tree. So that's an important property. Okay. So as we go through the algorithms, we'll build the minimum spanning trees, but let me illustrate the application of this property right away. There's an echo here, 1 second. Alright, so this is the given graph, and after we go through the algorithm, this is the minimum spanning tree we are going to end up with for this graph. Now let us pick up this edge weight. I'll finish this and give you time for asking question. 1 second. So if I remove this edge BE, it's going to partition them into two clusters. A, B, D, F is going to be one cluster, C, E, G is another cluster. So if you go back to the given graph, among the edges crossing the two clusters, so A, B, D, F is one cluster, C, E, G is another cluster. Okay, so the edges crossing the clusters are 8, 7, 15, 8 and 11. So among these 5 edges crossing the two clusters, so connecting the two clusters, 7 is the minimum edge weight. So 8, 7, 15, 8, 11. And 7 is the minimum edge weight. And the algorithm has picked up that edge that connects these two clusters. Okay, so that's the property of minimum spanning tree. Right? So with that, I'll stop and convert my video. So if you have any questions.